So this is the question in analysis of plain truss using direct stiffness method. Okay, so find the forces in the members of the truss, and the axial rigidity is same for all members. So there is a truss given A, B, C, D. So this is A, B, C, D. Four nodes are there, and this is 3 meter, 2 meter, 4 meter, 1.8 meter, 3.2 meter is the width, and there are two loads, 100 kilonewton and 80 kilonewton here at node A. Okay, so this is the question, and you are requested to find the forces in the members of the truss. So you have to find member force AB, AC, and AD. Okay, so there are three members AB, AC, and AD. I think the question is clear. So the procedure is same as that of direct stiffness method for continuous beams. Okay, only the difference is that you have to formulate the stiffness metrics in global coordinates. So in the continuous beams, there is only one coordinate system. All the direction of the axis of the beam is lying along with the global axis itself. But here the axis of each member is oriented in different directions. So you have to convert everything into a global direction. So that is the only difference between the continuous beam and truss problem. Okay, so now I'll move to the first step. First, as in the previous step, you have to find the kinematic indeterminacy or the degree of freedom, which is equal to 2. So here all the rotations and translations are arrested here also arrested, or you can use the basic formula to find the kinematic indeterminacy. Okay, so what is the formula? It is 2j minus r. 2 into j, 1, 2, 3, 4 joints, 4 into 2. 8 minus number of arrested, arrested degrees of freedom means 2 plus 2 plus 2, 6. So that means 8 minus 6 is equal to 2. Only the possible rotations are the translation at A and horizontal rotation at A. Okay, so these are the two possible, horizontal displacement at A and vertical displacement of joint A. So that are the two possible moments. So I have named the structure coordinates as 1, 2, 3, 4, 5, 6, 7, 8. At A, it's a global coordinates system. 1, 2, 3, 4, then 5, 6, 7, and 8. Okay, so these are the structure coordinates. I have named these are the structure coordinates. Now, D1, D2, D3, D4, D8 are the degrees of freedom, in which D3, D4, D5, D6, D7, and D8 are 0. Only unknowns are D1 and D2. Okay, only degrees of freedom are D1 and D2. And this is the same step as in case of continuous beam. So in step number 2, we will be finding the element stiffness matrix. But here you have to find in global coordinates. That's the only difference. We have to find that in global coordinates. So whenever you take each element, you have an expression for kg matrix. Kg of AB is AE by L into cos square theta sin theta minus cos square theta minus cos theta sin theta. And this 4/4 matrix you have to by heart. I have mentioned in the previous lecture. Okay, so this is the kg matrix. For that you require the theta. So what is theta? Theta is the angle that the axis of this member makes with the global x-axis. So this is the global x-axis, and this is a global x-axis. Okay, so 3. This is the x-axis in the global direction. So you have to find the angle that the axis of this member makes with the global x-axis in the anti-clockwise direction. So this is the angle here. So this is the angle that this member makes with the global x-axis. Okay, so this theta, this is theta. So you have to find theta as, so how will you find theta? You can use trigonometry and find the value theta. Okay, the total theta will be 90 plus this included angle. So this included angle you can find as tan inverse 1.8 by 3. So that is 126.87 degree. Okay, and this you can find sin theta, cos square theta, sin square theta, sin theta, cos theta, etc., of this angle 126.87 degree. KGAB you can find like this. Okay, so you can substitute the value AE by L. Length of the member is 3 meter, and substitute the values and find the you may take the 3 also inside. Otherwise, when we add different matrices, that will cause error. Okay, so you have to take this 3 also to inside of that matrix. So you'll get that matrix in the 4 by 4 form, AE into some matrix, and you have to name the coordinates 1, 2, 3, 4. Here it is 1, 2, 3, 4. So whenever you take the member AB, so this is A and this is B. So this is 1, 2, 3, and 4. Okay, so this is 1, 2, 3, and 4. 1, 2, 3, and 4. Okay, so you can substitute and find. Similarly, you can do it for element AC and element AD. So when you take element AC, so this angle theta is the angle that this vertical member AC makes with the global x-axis. So that theta is 90 degree. Okay, so you can find cos theta, sin theta, cos square theta, sin square theta, cos theta, sin theta, substitute in the equation, apply the value of L, take that L also into the matrix, and name the coordinates. It is 1, 2, 5, 6. So when you take AC, this member AC, so this is 1, 2, and 5 and 6. Okay, so this will be named 1, 2, 5, 6. Here 1, 2, 5, 6, 1, 2, 5, 6. Okay, so this cut is made in the next step only. So in the third element AD also you can take. AD is inclined like this. Here also you have to take the angle theta, that this global x-axis, and the member axis of the member. So in anti-clockwise direction, that theta is, there is no need to find theta. You can find cos theta, sin square theta, cos square theta, sin theta, cos theta. And substitute in the expression, apply the value of L, take that L value also into the matrix, and name the coordinates 1, 2, 7, 8, 1, 2, 7, 8. Okay, and this structure stiffness matrix in global. Next step is, so now you have found KGAB, KGAC, and KGAD, the global stiffness matrix. So that means the member stiffness matrix of each element is found in global coordinates by using the expression derived in the previous lecture. Okay, I think this is clear for you. In the third step, we can find the structure stiffness matrix in the global coordinates. Okay, so in global coordinates, you can find the structure stiffness matrix. So that is very important. So KG, sorry, this is not there. So delete rows and columns of arrested degree of freedom. I think I've missed that step. So AE into, you can add these all. Okay. This 1, 2, 3, 1, 2 corresponding, you can delete 3, 4 here, 3, 4 here, and you may add this 1, 2, 1, 2. Then for element AC also, this 1, 2, 1, 2, these 4 terms will be only remaining. Then here also you can delete for 7 and 8. Okay, and this 1, 2 only will be remaining, and you have to add, and you will get the matrix like this: AE into 0.28 minus 0.04 minus 0.04 and 0.72. Okay, I'll correct this and send you the PDF. I'll correct and send you. Okay, so I forgot to copy the matrix here. So this matrix is AE into 0.28 minus 0.04, then minus 0.04 and 0.72. Okay, so this is KG matrix. When you add all the 3 matrices, the corresponding coordinates, because only 1 and 2 remaining, all the others are deleted. Okay, and you have to delete rows and columns of arrested degrees of freedom. And in step number 4, as in the previous problem, you have to find the load vector as P as P0 minus PF. And here PF, the fixed end moment part is 0. So there is no fixed end moment, PF is 0. And only P0 remaining, nodal loads remaining. So P0 is equivalent join load. It is at join 1 and 2, we have 180 kilonewton load in the question. So when you look, this is 100 kilonewton right direction and 80 downward. Okay, so but our direction of 1 is towards right and direction 2 is towards upward. So direction 2 is upward. Okay, this is 1 and this is 2. But 80 kilonewton is acting downward. So this is minus 80. So you can write P0 as 100 and minus 80. Okay, so P is again P0 minus PF. PF is 0, again P0 itself, 100 minus 80. That much kilonewton. Now we can solve kg into D as P. You know the matrix of kg. Then D is also known to you. Then kg into D is equal to P. P is 100 and minus 80. So D1 and D2 can find by solving the equation. So this 1 by AE into 344 and 1 by AE into minus 92 D1 and D2. So there's two equations. I mean AX plus BY is equal to C, that format, and you can solve using calculator, and D1 and D2 will get. Okay. And in next step number 5, axial force in members. So you can use the equation F is equal to, this is also we have discussed in the previous lecture, which is will be equal to D1 minus D3 into cos theta plus D2 minus D4 into sin theta into AE by L. So this is the expression. So we can take D3 and D4 are 0. So D1 into cos theta. D1 is 344 by AE. So I have added this 1 by AE outside, and this is minus 92 by AE. So AE I can take outside, and you can multiply this by AE by L, so that AE and this AE will get cancelled. This cos theta value of the corresponding element. For AB, the theta value is known to you. Cos theta and sin theta value of member AB has to be substituted over here. Okay, and you can find the value. So this is minus 93.33. When you take F member AC, so that member AC is also vertical like this. This is member A, point A, and this is C. So one is like this. Sorry, one is like this, two is like this, and 5 and 6 like this. Okay, so this D1 minus D5 into cos theta plus D2 minus D6 into sin theta is the expression into AE by L. Okay, and D5 and D6 are 0, and you can substitute the values of D1 and D2 and find the forces FAC. And here also I have obtained negative, so it is tension. So I'll for element AD, so this FAD is D1 minus, so same expression, and I have obtained this as compression. So you can mark the member force like this. Okay, this is 93.33 tension, and this is also 38.33 tension, and this is compression, pushing the joints, 55 kilonewton. Okay, is it clear?